Surface tension is defined as the tensile force acting on the surface of a liquid in contact with a gas or on the surface between two immiscible liquids such that the angle of such that the contact surface behaves like a membrane under tension. The unit is Newton per meter. Okay, and we'll find out the surface tension and its effect on liquid droplet. Consider a small spherical droplet of a liquid of radius r. The pressure force is equal to 4 sigma by d. So the equation shows that with a decrease of diameter of the droplet, pressure intensity inside the droplet increases. So this equation is derived considering the equilibrium. Then if you consider a soap bubble, the pressure is 8 sigma by d. Then consider a liquid jet. Considering the surface tensile force, the pressure inside is 2 sigma by d. And we'll see simple problems here. The surface tension of water in contact with air at 20 degrees Celsius is 0.0725 Newton per meter. The pressure inside a droplet of water is to be 0.02 Newton per centimeter square, greater than that of outside pressure. Calculate the diameter of the droplet of water. So sigma is 0.0725 Newton per meter. Pressure P is 0.02 Newton per centimeter square. And considering the expression P is equal to 4 sigma by D, diameter is 1.45 millimeter. Next problem, find the surface tension in a soap bubble of 40 mm diameter when the inside pressure is 2.5 Newton per millimeter square above atmospheric pressure. So diameter of bubble 40 mm, pressure 2.5 Newton per millimeter square. Using the expression P is equal to 8 sigma by D, surface tension is equal to 0.0125 Newton per meter. Another simple problem. The pressure inside a droplet of water of diameter 0.04 mm is 10.32 Newton per centimeter square. Calculate the pressure within the droplet if surface tension is given as 0.0725 Newton per meter of water. Diameter of droplet is 0.04 mm. Pressure outside 10.32 into 10 power 4 Newton per meter square. Using the expression P is equal to 4 sigma by D, you get the pressure as 0.725 Newton per centimeter square. Pressure inside the drop is equal to P plus pressure outside the droplet. It is 11.045 Newton per centimeter square. Then the next property is capillarity, and therefore the capillary rise in a small tube immersed in a liquid can be found out. First we'll see what capillarity is. Capillarity is defined as a phenomenon of rise or fall of a liquid surface in a small tube relative to the adjacent general level of the liquid when the tube is held vertically in the liquid. The rise of liquid surface is known as capillary rise, while the fall of the liquid surface is known as capillary depression. And we'll see that it depends on the specific of the liquid, diameter of the tube, and the surface tension of the liquid. So consider a small tube immersed in a container having liquid. The liquid rises by a height h. The angle of contact is theta. Surface tensile force is sigma. Considering the equilibrium vertical component of surface tensile force is sigma into pi d into cos theta. Weight is pi by 4 d square into h into rho into g. Equating both, okay, you get the expression for capillary raises 4 sigma cos theta by gamma d or rho g d. If it is water, the angle of contact is theta is 0 degrees. The expression is 4 sigma by gamma d or 4 sigma by rho g d. Similarly, the expression for capillary fall may be found out. In case of mercury, the level falls down. The angle of contact is approximately around 130 degrees. Exactly, it is around 128 degrees. And we'll see a simple problem here. Calculate the capillary rise in a glass tube of 2.5 mm diameter when immersed vertically in water, mercury. Take surface tension is equal to 0.0725 Newton per meter for water and 0.52 Newton per meter for mercury in contact with air. Specific gravity of mercury is 13.6, angle of contact 130 degrees. So we'll solve the problem. Density is 13,600 kg per meter cube. Capillary rise for water when theta is 0 degrees, h is equal to 4 sigma by rho GD is 1.18 centimeter or 11.8 mm. For mercury, angle of contact theta is 130 degrees. So using the expression h is equal to 4 sigma cos theta by rho GD, it is minus 0.004 meter, minus 0.4 centimeter or 4 mm depression. Minus value shows that the level goes down. Another simple problem. Calculate the capillary effect in millimeter in a glass tube of 4 mm diameter when immersed in water, mercury. The temperature of the liquid is 20 degrees Celsius and values of the surface tension of water and mercury at 20 degree centigrade in contact with the air are 0.035575 Newton per meter and 0.51 Newton per meter respectively. Angle of contact 0 for water, mercury 130 degrees. Density of water, take it as 20 degrees Celsius, take it as 998 kg per meter cube. So we'll solve the problem. Expression is 4 sigma cos theta by rho g d. Capillary effect for water, h is substitute in that all the values to get it as 7.51 millimeter. Capillary effect for mercury, to the same expression, cos 130 being negative, you get minus 2.46 into 10 power minus 3 meter. It is minus 2.46 millimeter. That is, it goes down, depression. Another simple problem, the capillary rise in the glass tube is not to exceed 0.2 millimeter of water. Determine its minimum size. Given that the surface tension for water in contact with air is 0.0725 Newton per meter. So h is 0.2 mm, surface tension is 0.0725 Newton per meter. Take the diameter as d, substitute in the expression h is equal to 4 sigma by rho gd. You get the diameter as 0.148 meter, that is 14.8 centimeter. Another simple problem, determine the minimum size of glass tube that can be used to measure water level if the capillary rise in the tube is to be restricted to 2 millimeter. Consider surface tension of water in contact with air as 0.073575 Newton per meter. So capillary rise is 2 millimeter, sigma 0.073575 Newton per meter, diameter d, theta is 0 degree for water, rho 1000 kg per meter cube. Substitute in the expression h is equal to 4 sigma by gamma d, you get the diameter as 0.015 meter, that is 1.5